Hi and Assalamualaikum. Today, our group will present to you about insect classification of bees and butterfly using image processing with manual KNN classifier. First of all, I will introduce to you our group members. The first one is myself, Nopuchi Madam Ashikin binti Sharunizam Elias Mus. The second one is Fatin Nadira binti Abdul Hadi. The third members is Siti Aina Zulaika binti Zaini. And the last one is Wan Muhammad Daniel bin Wan Muhammad Farid. There are two types of insects that we choose, which is bees and butterflies. Insect classification is a crucial task in fields such as agriculture, ecology, monitoring and biodiversity research. Traditionally, this process relies on manual identification, which is time-consuming and requires expert knowledge. With advance in computer vision, automated classification using image processing has become more efficient and accessible. This project explores a simple yet effective approach by using basic image processing techniques in MATLAB, combined with a manual implemented K-nearest neighbor (KNN) classifier by extracting and analyze morphological features such as area, perimeter, and eccentricity. The system can accurately distinguish between bees and butterflies. This method is particularly useful in low research settings where simplicity, interpretability, and efficiency are essential.
Our project aims to develop a MATLAB-based insect classification using KNN classifier, and for significance, our system uses MATLAB image processing tools to help solve big problems in bug study, especially in poor areas without expensive machines. The system makes insect identification easy for users while keeping results perfectly correct. It is useful for both educators and students and may help us understand insects better globally. Before we can classify insects, we need to prepare the images to highlight the important details. This is the tricky pre-processing step we use to clean up and focus each image. First, we convert the colorful RGB image to grayscale using MATLAB RGB2 gray function. This simplifies the image by removing color and keep all the essential shape and texture of the insect. Next, we boost the contrast using IMHs to make the insect stand out clearly against the background. Then, we apply the solver edge detection, a fancy term for highlighting the insect outline. This step is like tracing the edges of the insect with the highlighter so the computer can easily see the shape. Finally, we convert the image to pure black and white using OutZoom method, a smart way to automatically decide the best threshold. This step acts like a stencil, leaving only the insect outline and removing all noises background.
Alright, I will represent the classification. So classification using the K-nearest neighbor KNN. So I show up the formula. This formula for D is the Euclidean distance between the test and training the feature vector. XY and XI and YI are the normalization feature value for the test and training, the sample respectively. And for the N is the total number of the feature user, which is the included area, parameter, and eccentricity. In the process, number 1 is calculate the distance between the test and all training image. 2. Solve the distance in the NCP order. 3. Select the 3 nearest neighbor. And the last one, the 4, predict the class based on the most frequent label among them. So for the advantage for the classification, my team are using the KNN. So first, the transparent and easy to debug. No training space the required. Efficient for the low power or limit resource at the system. Flexible and useful for the learning or the customization. The accuracy, the calculations. Will we see the formula, the accuracy, number of correct prediction, divide the total number of the prediction multiply for the hundreds. So how the it will work? First, the classifier make the predictions for the test image. 2, its prediction is compared to the actually true level of the image. And number 3, the number of the correct prediction is counted. 4, divide by the total number for test image. And lastly, multiply by 100 to get a percentage. We use the accuracy as a performance metric to evaluate of the classification model. After training, we 80% of the image we tested the model on the remaining to 20%. We then compare the prediction insert type to the correct label of the test image. In our case, all test images were correctly classified, so the model achieved 100% accuracy. However, this doesn't mean the model is perfect. It just means it worked well on the small thing that as I said, for the more reliable result, we will need to test the model with more the varied and real world.
Now we will continue to the testing phase of our insect classification system. This testing phase includes 3 main steps, which is image preprocessing, feature extraction, and classification. First, in the image preprocessing, each test image is converted to grayscale using RGB to gray function. Then we enhance the image contrast with the IM adjust to improve visibility. To isolate the insect from the background, we apply also thresholding using IM binarize. Then the edge detection is also performed to help visually analyze the insect's shape, although this step is optional. Next, in the feature extraction stage, we focus on calculating morphological features from the segmented binary image. These include the insect's area, perimeter, and eccentricity. These features are extracted using the region props function, which provide critical information about the object shape. These descriptors help to differentiate between bees and butterfly. Finally, in the manual classification steps, we use the custom k-nearest neighbors, which is KNN algorithm, with the k equal to 3. So for each test image, we calculate its Euclidean distance from every training sample based on the normalized features values. Then we identify the 3 closest training sample using the majority voting to assign the final class label. To conclude, this project successfully demonstrated that traditional image processing techniques combined with a manually implemented k-nearest neighbors classifier can effectively classify insect images, especially distinguishing between bees and butterflies. The system achieved 100% accuracy rate on a small, well-controlled dataset, highlighting its effectiveness under ideal conditions. Its simplicity and low computational demand make it highly suitable for educational purpose and application in low-resource environments. That said, for this method to be applied more broadly in the real-world scenario, future improvement should be involved testing the model on larger and more diverse datasets. This would help ensure the system robustness, scalability, and adaptability when dealing with more complex and variable insect